Most stars do not burn bright. They burn quietly, patiently, and for longer than almost anything else in the universe. Red dwarfs may be the smallest true stars, but one day they could outlive every star we know, become the last warm homes in a fading cosmos, and perhaps even offer the best chance for life to endure into the far future. If that sounds like your kind of science story, please take a moment to like the video, subscribe to the channel, and share it with someone who loves space and cosmic mysteries. And thank you, as always, for being here. Before we begin, I'd love to know what time is it where you are, and from which part of the world are you listening? Please leave a comment below. Now, let's begin our journey into the quiet, ancient future of red dwarfs. A red dwarf does not announce itself. It does not dominate the sky the way bright blue stars do in photographs, and it does not command the imagination the way a supernova or a black hole does. In most cases, it would barely seem worth noticing at all. It is small by stellar standards, cool at the surface compared with stars like the Sun, and so dim that none can be seen with the unaided human eye from Earth, even though they are among the nearest stars to the solar system. And yet this quiet, diminished appearance hides one of the most important facts in all of astronomy. Red dwarfs are not rare background objects tucked away at the margins of the universe. They are the main stellar population. The Milky Way is filled with them. Other galaxies are filled with them. By count, they are the ordinary stars of the cosmos, even if ordinary is not the word their long future invites. When astronomers classify stars by mass, temperature, and brightness, red dwarfs fall into the smallest range that still permits steady hydrogen fusion in the core. That makes them true stars, not failed ones, but only just. They sit near the lower edge of what nature allows to shine by nuclear fire. And because the universe forms far more small stars than large ones, it produces red dwarfs in overwhelming numbers. The grand luminous beacons that shape familiar constellations are, in a deeper statistical sense, the exception. The faint, cool stars that human eyes cannot pick out are the rule. This changes the scale of the subject immediately. A red dwarf is not a curiosity on the side of stellar evolution. It is one of the dominant outcomes of it. The night sky, as it appears from Earth, gives a misleading impression of what the universe is made of, because human vision favours brightness, and brightness favours the uncommon. A massive star can outshine countless smaller ones. A nearby hot star can make itself known across a large stretch of sky. But red dwarfs keep their light to themselves. Their radiation is modest. Their glow leans heavily toward the red and infrared part of the spectrum. Their visibility drops below the threshold of unaided sight long before distance becomes truly large. So the sky that seems full of brilliant points is, in an important way, incomplete. Hidden behind that visible layer is a far larger population of dim stars, scattered through space in numbers so great that the galaxy would be unrecognizable without them. The nearest stellar system to the Sun offers a useful example. Proxima Centauri, the closest known star to Earth beyond the Sun, is a red dwarf. It is closer than any other star, yet it is still invisible without a telescope. This is not because it is distant in any ordinary sense. On a galactic scale, it is almost next door. It is invisible because red dwarfs are intrinsically faint. That distinction matters. It means the universe can place one of its most common stars directly in the local neighborhood and still keep it hidden from casual view. It also means that human beings, for most of their history, lived beneath a sky that concealed the majority of its own stellar inhabitants. Only with instruments sensitive enough to detect weak light did the true pattern begin to emerge. Once surveys improved, and once astronomers could map nearby stars with greater precision, the local census started to reveal what theory already suggested red dwarfs are everywhere. In the immediate neighbourhood of the Sun, they make up most of the stars. In the galaxy as a whole, they likely account for roughly 3/4 of all stellar objects. This is not a minor numerical edge. It is a structural fact about how the Milky Way is built. It means that when gas clouds collapse and fragment to form new stars, nature strongly favours the small over the spectacular. Mass is difficult to gather. Extreme brightness is costly. The long-lived middle and lower ranges are easier to produce, and the lowest true stellar range is where red dwarfs reside. Their masses begin at just above the threshold required for sustained fusion, only a little heavier than the limit below which an object becomes a brown dwarf, and extend upward to about half the mass of the Sun. That upper boundary is still enough to be a real star in every meaningful sense. But it is far from the scale people tend to picture when they think of stellar power. Some of the smallest red dwarfs are only slightly larger than Jupiter in diameter, despite containing vastly more mass. Their matter is compressed into compact, dense interiors, and their surfaces radiate with such restraint that even when they are numerous, they do not easily dominate a scene. There is something almost deceptive about that combination. A red dwarf is not tiny in any human sense. It is still a sphere of hot plasma, immense beyond ordinary comparison, held together by gravity and sustained by nuclear fusion. But next to the Sun, and especially next to giant stars, it seems reduced to essentials, like a star stripped down to the minimum design that still works. That economy is part of its importance. The universe appears to have no shortage of ways to make brilliant, short-lived stars, but it produces far more of these efficient, modest burning ones, as if long endurance and low output are among the favoured arrangements of cosmic matter. This is one reason red dwarfs have moved from obscurity to central relevance in modern astronomy. The more closely researchers examine the architecture of the galaxy, the more impossible it becomes to ignore the stars that do most of the existing. A map of visible light does not tell the whole story. A map of stellar demographics tells a different one. And in that version of the cosmos, red dwarfs are no longer faint side notes. They are the background population against which much of galactic history unfolds. They fill old stellar neighbourhoods. They persist through changing eras of star formation. They accumulate across time. Their abundance also changes how the search for planets and life must be framed. If most stars are red dwarfs, then most planetary systems may orbit red dwarfs too. If the nearest stars are often red dwarfs, then the nearest rocky worlds are likely to be found around them. The question is no longer whether these stars matter, but how many of the universe's future possibilities may depend on them. That future begins with a simple observational correction. The cosmos is not mainly composed of the stars most easily seen. It is mainly composed of stars that withdraw from view, stars that radiate with caution, stars that seem minor until their collective presence is counted. Even their colour contributes to this impression. The term red dwarf can sound almost gentle, as though it refers to something weak or fading, but the colour comes from temperature and not from age. These are cool stars, not dying ones. Their surfaces are often only a few thousand degrees above absolute zero, significantly cooler than the Sun, and that lower temperature shifts their emitted light away from the intense visible output associated with hotter stars. As a result, they glow with a subdued reddish cast and strong infrared emission, a signature more apparent to instruments than to human sight. What looks dim to the eye may still be a stable, active star. What looks negligible in the sky may still outnumber nearly everything else in it. That inversion is the real entrance to the subject. Red dwarfs teach a lesson that appears again and again in astronomy. Visibility is not the same as importance, and brightness is not the same as dominance. The stars that will matter most over the longest stretches of time are not necessarily the ones that define the present sky. They are the ones that endure in silence, repeating the same restrained process across ages so large that even galaxies begin to change around them. Before their internal physics is examined, before the strange possibilities of their planets are weighed, before their unimaginable lifespans are followed into the remote future, there is this first essential fact to absorb. The universe is crowded with small stars that hardly seem to shine at all. They are close, numerous, and usually hidden. They occupy the local stellar landscape in numbers far beyond intuition. And once that hidden majority comes into focus, the familiar picture of the cosmos begins to shift. The bright stars become the temporary exceptions. The faint ones become the durable rule. Among those quiet, easily overlooked stars may lie not only many of the galaxy's worlds, but the deepest reserve of starlight the future will ever have. Near the lower edge of starlight, the difference between success and failure becomes remarkably small. A cloud of gas can collapse under its own gravity, gather mass, heat itself through compression, and still fall short of becoming a true star. That narrow divide is where red dwarfs begin. They occupy the smallest mass range in which hydrogen fusion can sustain itself over immense spans of time, and because of that they stand at one of the most interesting thresholds in astrophysics. Below them lie brown dwarfs, objects often described as failed stars. Though the phrase is slightly unfair, brown dwarfs are not mistakes. They form much like stars do, from collapsing clouds of gas, and in their youth they can glow with considerable heat. Some can briefly fuse deuterium, a heavier form of hydrogen, and the more massive among them may also fuse lithium for a time, but they never achieve the stable, long-term hydrogen burning that defines a true star. Their interiors warm, their early brightness fades, and over time they settle into gradual cooling. A red dwarf begins only a little farther up the scale, with just enough mass for gravity to push the core to the temperature and pressure required for ordinary hydrogen fusion to continue. That is the crucial step. It is not a large leap in appearance, and not even a large leap in size, but physically it changes everything. One object is destined to cool from its birth onward. The other becomes a self-sustaining star whose life can extend for trillions of years. The threshold itself depends on composition, especially the amount of hydrogen and heavier elements present. But for ordinary stellar matter it falls at roughly 1/10 of the Sun's mass, slightly less in many estimates. That number sounds modest, yet the consequences are absolute. Nature permits no negotiation there. An object below the threshold can contract, shine faintly, and mimic a star in some respects, but it will not settle into the same kind of long-lived equilibrium. An object above it joins the stellar population proper. Red dwarfs are therefore the minimum working version of a star, not the dimmed remnant of something greater, but the first durable form that nuclear fire can take. This makes them valuable far beyond their faintness. They reveal how close the universe can come to extinguished matter before fusion still manages to hold on. They are the answer to a precise question: how little star can a star be and remain a star at all? That answer carries an unexpected visual consequence. For all the difference in mass between the smallest red dwarfs and the largest gas giant planets, their diameters are not dramatically different. A red dwarf near the lower mass limit may be only somewhat larger than Jupiter. This can seem almost absurd at first. A true star, powered by fusion, sounds as though it should tower over any planet by a vast margin. Yet size is not controlled by mass alone. Matter under intense pressure behaves in ways that are not intuitive at everyday scales. In both giant planets and the smallest stars, compression changes the relationship between mass and radius. Add more matter, and the object does not simply grow wider in proportion. Gravity presses harder, density increases. The result is that an object with many times Jupiter's mass can still occupy a surprisingly similar volume. This is one reason the smallest red dwarfs appear so conceptually delicate. They're not dainty in any literal sense, but they live right beside giant planets on the scale of physical dimensions while differing profoundly in internal state. Jupiter is enormous, but it is still a planet, with no sustained fusion in its interior. A minimal red dwarf may look only modestly larger, and yet deep within it hydrogen is being fused into helium. That hidden distinction is the whole story. What matters is not the outer impression, but the condition at the core. Gravity has done just enough work. The interior has crossed the line. The object has moved from compressed planetary matter into the slow-burning category of stars. There is a certain elegance in that economy. The universe does not require grandeur to produce starlight. It only requires enough mass in one place for pressure to transform a dense sphere of gas into a stable nuclear engine. The smallest red dwarfs embody that principle with unusual clarity. They are close to planets in radius, close to brown dwarfs in mass, close to the failure boundary in formation history, and yet once established they belong to a very different future. Brown dwarfs cool, red dwarfs endure. This threshold also matters because it shapes how astronomers think about the census of objects between planets and stars. The sequence is not neatly divided into visually obvious categories. Instead, it forms a progression from giant planets to brown dwarfs to the smallest red dwarfs, with each step defined less by appearance than by internal physics. A massive planet may retain heat from formation and emit infrared radiation. A brown dwarf may look faintly stellar in a young system. A tiny red dwarf may barely exceed them in size. Only careful measurement of mass, temperature, luminosity, and spectral features reveals which side of the line an object occupies. In that sense, the lower edge of the stellar population is not a place of dramatic visual contrast. It is a place of subtle but decisive physical distinctions. That subtlety has practical importance for observation. Many of the nearest and faintest objects found in stellar surveys must be examined with care because the boundary region is crowded with ambiguous cases. An object can be dim because it is small, dim because it is old, dim because it never became a star, or dim because it did become a star but only barely. Distinguishing among these possibilities requires more than brightness alone. Astronomers use spectroscopy to study the light an object emits and absorbs, looking for clues to temperature, chemical makeup, gravity, and age. They model how such objects evolve. They compare observed properties to theoretical tracks. Out of that slow process comes a more reliable classification, and with it a better understanding of how red dwarfs populate the galaxy's lower stellar ranks. This is where the concept of the failed star becomes useful again, provided it is handled carefully. A brown dwarf is not failed in the emotional sense, but in the technical sense it does fail to reach the main sequence, the long stable phase in which hydrogen fusion balances gravity. Red dwarfs, by contrast, do reach it, even the very smallest among them. Their low mass means their cores are cooler than those of larger stars, and their fusion reactions proceed far more slowly, but slow is not absent. The process holds. Gravity presses inward, pressure and heat maintain fusion, and the released energy pushes outward. An equilibrium forms, the star settles. That balance may be delicate compared with the more forceful internal conditions of larger stars, yet it is strong enough to survive across timescales that dwarf the current age of the universe. In that respect, the smallest red dwarfs are almost paradoxical. They stand nearest to failure at the beginning and nearest to permanence in the long run. Their slight advantage over brown dwarfs turns into one of the greatest advantages any star can possess: longevity. To understand red dwarfs properly, it helps to resist the instinct to rank them by spectacle. Larger stars seem more impressive because they are brighter, hotter, and often more violent. But the threshold objects at the bottom tell a different story about what the universe values over time. They show that once a body crosses the minimum line into true fusion, even by a narrow margin, it can secure a place in cosmic history far out of proportion to its size. A massive blue star may burn with enormous brilliance and die within a relatively brief period. A minimal red dwarf begins with almost no excess at all, and then continues, patiently, for spans so long that words like ancient begin to lose precision. That future is built on the smallest surplus of mass above the fusion threshold, a margin so narrow that the category almost trembles at its edge. This is why the lower limit of starlight deserves more than a technical footnote. It is not only a boundary in classification, it is a boundary in destiny. On one side lie objects that glow for a while and then fade. On the other lie stars so restrained that the universe has not yet seen any of them grow old. The smallest red dwarfs are the first members of that enduring class. They are the least extravagant stars the cosmos can make, almost planetary in size, almost substellar in mass, almost too slight to count. And yet once their cores ignite, the question of whether they are truly stars disappears. What remains is the deeper fact that the universe forms them in vast numbers, and that many of its longest futures begin precisely at this narrow, easily overlooked threshold. Inside a red dwarf, the crucial event is not brightness but circulation. A larger star like the Sun is layered in a way that keeps much of its helium locked deep in the centre. Once hydrogen there has been fused, the core changes first, the outer regions later, and the star's future unfolds through a kind of internal separation. A red dwarf is built differently. In many of these small stars, especially the lower mass ones, hot material rises and cooler material sinks throughout most or all of the interior in a continuous churning motion known as convection. That movement is not a surface detail. It is the defining advantage of the star. It means that fuel is not confined to one narrow region and then cut off from the rest. Hydrogen from farther out can be carried inward over time, while helium produced by fusion is mixed back through the star instead of piling up in a single exhausted core. The result is one of the most efficient stellar designs the universe produces. A red dwarf does not burn fiercely, it burns thoroughly. That distinction matters more than almost any other fact about its future. In a more massive star, gravity presses inward with greater force. The central temperature rises to more extreme levels, and fusion runs much faster. Energy production becomes intense, and that intensity gives the star its brilliance. But the price of brilliance is waste. A larger star often consumes only a limited fraction of its total hydrogen during its stable life, because much of that hydrogen never reaches the core in time to be used before the structure changes. In effect, the star is wealthy in fuel, but poor in access to it. A red dwarf has the opposite arrangement. Its gravity is gentler, its core temperature is lower, and its fusion reactions proceed at a far more measured pace. It generates much less light, but it also avoids the internal bottleneck that causes larger stars to leave so much potential fuel untouched. Through convection, the star behaves less like a layered furnace and more like a slowly stirred reservoir, bringing fresh hydrogen into useful regions over spans so long that the entire logic of stellar aging changes. This is why red dwarfs are often described as miserly, though the word suggests intention where there is only physics. The star is not choosing restraint. Its mass determines the pressures in its core, and those pressures determine the temperature, and that temperature determines the rate of fusion. Everything follows from being small. Nuclear fusion is enormously sensitive to conditions. Raise the core temperature and reaction rates increase sharply. Lower it, and the process slows to an almost patient crawl. In a red dwarf, the inward pressure is sufficient to sustain hydrogen fusion, but not sufficient to drive it at anything like the pace seen in more massive stars. These stars live near the minimum threshold of starlight, and their internal engines reflect that economy at every level. Their luminosities can be a tiny fraction of the sun's. Their power output is modest. Their rate of fuel consumption is correspondingly low. Yet the star does not simply drift in weakness. It maintains a stable balance between gravity and fusion for spans of time that no larger star can match, because it asks so little of its fuel at any given moment and uses so much of what it has. The mechanism itself is elegant. Convection begins when energy cannot move outward efficiently by radiation alone. In such conditions, parcels of hot plasma rise because they are slightly less dense than their surroundings, while cooler material sinks. This overturning repeats constantly, carrying heat outward and matter inward and outward in a single coupled process. In the Sun, convection dominates only in the outer envelope, while the deeper interior includes a radiative zone that does not mix its material in the same way. In many red dwarfs, especially the smaller ones, convection can extend through nearly the whole star. That means the line between core and envelope becomes less absolute than it is in stars like the Sun. Fusion still occurs in the deepest and hottest regions, but the star's matter remains in conversation with itself on a much larger scale. Fuel is not trapped by structure. Structure is what helps keep the fuel available. This changes the meaning of stellar lifetime. When people imagine a star running out of fuel, the image is often simple. The star burns through its hydrogen and then begins to die. But in practice, the phrase running out can mean different things. A star may exhaust the hydrogen in its core while still containing enormous amounts of hydrogen elsewhere. What matters is not merely how much fuel exists, but whether the star can deliver that fuel to the places where fusion can continue. Red dwarfs solve that transport problem unusually well. They can use a very large fraction of their hydrogen over the course of their main sequence lives, far more than stars like the Sun. This is one reason their lifespans become so extraordinary. Another is that the fuel is spent under such cool, subdued conditions that each step takes an immense amount of time. The red dwarf is both efficient and slow, a rare combination in astrophysics, where efficiency often accompanies intensity, and intensity often shortens life. Here, the opposite holds. A small, fully convective star turns low power into almost unimaginable endurance. The timescales involved are difficult to hold in mind. The Sun, though stable on human terms, has a main sequence lifetime measured in billions of years. A red dwarf can remain on the main sequence for trillions of years, and the smallest among them may survive for even longer than that. This is not because they contain more fuel in an absolute sense. They do not. It is because they waste so little and demand so little. A larger star behaves like a bright flame that consumes its fuel with urgency. A red dwarf resembles a deeply banked fire that never hurries and rarely loses energy to excess. Even its outward appearance reflects that inward restraint. These stars remain faint not because they are dying, but because they are operating at low intensity by design. Their dimness is not a weakness of age. It is the visible sign of a conservative engine. That engine also gives red dwarfs an unusual kind of stability in cosmic terms. Massive stars live violently and die dramatically because the conditions required to support their great luminosities also prepare them for rapid structural change. Their cores evolve through successive fusion stages, their envelopes expand, and their final acts can include collapse, explosion, or the production of neutron stars and black holes. A red dwarf does not move through that sequence. It never reaches the internal temperatures required to fuse heavier elements in the same cascading way. It remains in the hydrogen-burning phase for so long that the rest of stellar evolution is deferred into a future the universe has not yet reached. This means that every red dwarf that has ever formed is still, in essence, in its long central act. None have completed the full journey. None have exhausted the stable hydrogen-burning life that convection helps sustain. In that sense, red dwarfs are not merely long-lived stars. They are stars whose later history remains theoretical because time itself has not yet supplied an example. Models show what should happen. Physics points to the path ahead. But the universe is still too young for direct confirmation. That gives red dwarfs a quiet strangeness. They're among the most common stars in existence, yet their full biographies remain unwitnessed. All that hidden longevity depends on the internal motion that keeps them mixed. If red dwarfs had the same layered fuel economy as larger stars, their lives would still be long, but not remotely as long as they are. Convection is what turns small mass into vast duration. It allows the star to keep drawing on its hydrogen supply far beyond what a more segregated structure would permit. In a way, the star's modesty at the surface is purchased by extraordinary discipline beneath it. Heat rises, matter circulates. Hydrogen is carried where it can still matter. Helium does not immediately form a dead central burden. The whole star participates, slowly, in sustaining the core conditions that let fusion continue. Nothing about this process is dramatic in the usual sense. There are no sudden reversals, no eruptions required for the basic design to hold. The power of the system lies in its refusal to rush, and because the engine is so restrained, red dwarfs become more than a category of stars. They become repositories of future time. They preserve usable starlight across stretches of cosmic history that all brighter stars will fail to reach. That is why their internal physics matters so deeply. The question is not only how these stars shine, but how they go on shining when nearly everything more luminous will have already faded. The answer begins with a simple movement repeated through the whole body of the star, rising, sinking, mixing, carrying fuel inward and products outward, turning what should have been a limited reserve into a nearly inexhaustible one by stellar standards. A red dwarf does not win its future through power. It wins through access, balance, and patience. The surface glow may look slight. The engine beneath it is one of the most durable arrangements matter has ever found. Once that is understood, red dwarfs no longer seem like reduced versions of ordinary stars. They appear instead as a different solution to the problem of how a star can live, one built not for brilliance, but for time itself. The universe is old enough to have erased oceans, rebuilt continents, merged galaxies in progress, and filled interstellar space with the ashes of dead stars. Yet it is still too young to show a single elderly red dwarf. That imbalance is one of the strangest perspective shifts these stars create. Cosmology often teaches age through immensities. The universe is about 13.8 billion years old. The Milky Way has existed for most of that span. Many of its stars were born long before the Sun. Entire generations of massive stars have formed, burned brightly, exploded, and vanished. Even stars with far longer lives than the Sun have had time to change substantially. And still, every red dwarf ever formed remains in the earlier stable phase of its existence. Not one has finished the long hydrogen-burning life that defines its central history. Not one has entered the late stages that theory predicts. In human terms, in planetary terms, even in galactic terms, these stars seem ancient. In their own terms, they are still only beginning. This is not because red dwarfs form unusually late. Many are extremely old. Some likely appeared when the universe itself was much younger. and star formation conditions were different from those in the present Milky Way. The reason none have aged into their final acts is simpler and more profound. Their clocks run on scales so extended that the current age of the cosmos covers only the first fraction of their main sequence lives. A star like the Sun is expected to remain stable for roughly 10 billion years in total, a span that already seems almost without limit when measured against the history of life on Earth. Yet a small red dwarf can endure for trillions of years. That is not merely longer by a comfortable margin. It is longer by factors so large that ordinary comparison begins to fail. The Sun's whole stable lifetime fits within the future of a red dwarf the way a single chapter fits inside a vast archive. This changes the meaning of cosmic youth. Usually, age in astronomy is attached to distance, to erosion, to cooling, or to the remnants of exhausted processes. But red dwarfs reveal that an object may be ancient in origin and youthful in evolution at the same time. A red dwarf born 10 billion years ago is older than the Sun by nearly half the age of the solar system. Yet it has still not moved beyond the stellar equivalent of an extended beginning. It remains on the main sequence, still fusing hydrogen, still structurally stable, still far from the transformations that mark true stellar old age. The phrase "every red dwarf is still a baby" is not literally correct in chronological terms, but it captures something real about the mismatch between cosmic time and stellar development. These stars age so slowly that the universe has not yet lived long enough to witness their maturity. There is a useful contrast here with more massive stars. A star many times heavier than the Sun lives fast because its internal pressures and temperatures are extreme. It races through fuel, evolves quickly, and may die in only millions of years. Such a star can complete its full life cycle, while a red dwarf of similar birth date has barely settled into the routine that will define most of its existence. Even the Sun, with its moderate pace, has already progressed far enough that astronomers can model its future with confidence based on observations of other stars at comparable stages. Red dwarfs do not offer that same observational completeness. Their later evolution is inferred from stellar physics, not directly seen in nature. That alone makes them unusual. Astronomy is often a science of comparison. One star can be understood by looking at many others slightly earlier or later along the same path, but for red dwarfs, the universe has not yet provided the older examples. The sequence ends, for now, inside theory. This gives red dwarfs a rare status. They are among the best understood stars in terms of their internal principles, and yet among the least completely observed in terms of full life history. Their future is known in outline, but not in the direct way astronomers prefer, by seeing nature already carry it out. The reason is not a lack of red dwarfs, it is a lack of time. Time itself has not advanced far enough for evidence to arrive. That fact becomes even more striking when placed against the age structure of the universe. The earlier stars were not red dwarfs in the ordinary modern sense alone. In the very first stellar generations, conditions favoured stars with unusually low amounts of heavy elements, and the first stars may have been much more massive on average than those forming later. Massive primordial stars would have lived briefly and died long ago, enriching the cosmos with heavier elements through their deaths. Those elements then helped shape later generations of stars and planets. Among those later generations, red dwarfs became abundant and persistent. Many that formed billions of years ago are still present in the galactic disk and halo, carrying within them a record of earlier cosmic conditions through their chemical composition. Yet chemically old does not mean evolutionarily old. A red dwarf can preserve the signature of a much earlier era while remaining physically far from exhaustion. It is a kind of long memory embedded in a still young engine. This has consequences for how cosmic history is imagined. The present universe is often called the stelliferous era, the age in which stars still shine in large numbers, That phrase suggests a middle time, a bright age between the early fire of the cosmos and the eventual fading of all ordinary starlight. Within that broad era, red dwarfs already hold a special place, because they are not simply participants in the current age, they are the reserve that will outlast it. Massive stars belonged most strongly to the universe's energetic youth. Sun-like stars belong to the long but finite middle. Red dwarfs stretch onward into a future so distant that the current epoch begins to look preliminary by comparison. From their perspective, the bright present is only the opening portion of a much longer story. This is why no old red dwarfs exist yet in the observational sense. Old age for such stars belongs almost entirely to the future universe. It has not yet entered the historical record. That absence does not make the stars static. Red dwarfs do change, but so slowly that the changes are subtle within the span of current cosmic time. Their luminosities and temperatures shift gradually as they fuse hydrogen and alter their internal composition. Over immense periods, a red dwarf can become somewhat hotter and brighter rather than dimmer, because changes in the interior affect how energy is produced and transported. This is another reminder that their apparent simplicity is deceptive. A red dwarf is not frozen in one perfect state forever. It evolves, but it does so with such restraint that even billions of years do not carry it into any dramatic late-life transformation. The star remains recognizably itself. It does not swell into a red giant the way the sun eventually will. It does not rush toward collapse. It continues, slowly adjusting while still inhabiting the same fundamental stage. That continuity makes present-day red dwarfs seem almost outside ordinary aging, though in truth they are simply aging on a scale that makes the age of the universe look short. There is something quietly unsettling in that reversal. Human beings naturally treat the universe as the largest timescale available, the final backdrop against which all other durations are measured. Red dwarfs disturb that instinct. They do not outlast the universe itself in any absolute sense, but their main sequence lives extend so far beyond the current cosmic age that the universe, as presently experienced, becomes only their youth. The familiar stars of the sky are temporary companions in that comparison. The sun is middle-aged in a way red dwarfs are not. Giant stars are brief flashes. Even many white dwarfs already exist as remnants of stars that completed their active lives, while red dwarfs remained at the start of theirs. The cosmos, vast as it is, has not yet caught up to these faint stars. This also means that when astronomers study red dwarfs today, they are studying not the completion of a stellar strategy, but its early promise. All known red dwarfs are first-act stars. Their real distinction lies not in what they have already done, but in what they are still capable of continuing to do long after brighter stars are gone. The current universe contains their infancy, their persistence, and the opening stretch of their endurance, but not their decline. That missing evidence is not a flaw in knowledge. It is a measurement of scale. To say that no red dwarf has yet reached old age is to say that the future history of starlight is still largely waiting inside the dimmest stars around us. They have existed through much of cosmic time already, yet cosmic time itself has barely begun to test them. In that sense, red dwarfs are not simply relics of stellar formation. They are previews of the far future, early enough in their own lives that the universe must continue for unimaginable ages before their real aging will even start to become visible. Around a red dwarf, the habitable zone does not sit at a comfortable distance. It presses inward, close to the star, because the star itself gives off so little energy that any planet hoping to keep liquid water at the surface must orbit near the source of that warmth. This is the first great shift red dwarfs impose on the usual picture of a life-friendly world. In the solar system, Earth circles far enough from the sun to avoid the worst extremes of solar heating, while still receiving enough energy for oceans, weather, and long-term climate stability. Around a red dwarf, that same balance must often be found much nearer and sometimes at distances more comparable to Mercury's orbit than to Earth's. The geometry of habitability changes. A zone that sounds gentle in principle becomes physically compressed, narrow enough that a small change in distance can matter greatly. Too far out, and water may freeze across the surface. Too far in, and the planet risks heating beyond recovery. The idea of a habitable zone remains useful, but around red dwarfs it becomes less like a broad ring of opportunity and more like a close boundary where favourable conditions exist beside very serious complications. This nearness is not accidental. A red dwarf is cool and dim because its surface temperature and total luminosity are much lower than those of the Sun. That means its energy spreads outward from a weaker source. By the time that energy reaches a world at Earth-like distance, there is not enough of it to support familiar surface conditions, so the planet must move inward. It must orbit quickly, often completing a year in only days or weeks, tucked into a region where the star looms larger in the sky and gravitational effects become harder to ignore. At first glance, this might seem encouraging. If red dwarfs are so common, and if rocky planets are common around them, then an enormous number of worlds may exist in these close habitable zones. Modern planet surveys support that broad impression. Small planets appear to be frequent around small stars. Many of the nearest known rocky exoplanets orbit red dwarfs simply because those stars are numerous and because close-in planets are easier for astronomers to detect. A planet passing in front of a small star blocks a relatively larger fraction of its light than the same planet would block around a larger star, making transit signals more noticeable. The gravitational pull of an orbiting planet also produces a stronger observable effect on a low-mass star. In this sense, red dwarfs have become natural laboratories for exoplanet science. They present planetary systems in a way that observation can reach more easily. But detectability is not the same as comfort. The very closeness that makes these planets easier to find is also what makes them difficult to understand as homes. A world in the habitable zone of a red dwarf does not merely receive less light from a smaller star, it lives deep inside the star's gravitational influence, in a region where orbital locking, stellar activity, and long-term climate pressures all become more intense. The habitable zone is therefore not a promise, it is a starting condition. It says only that average surface temperatures might allow liquid water under the right circumstances. It does not say the atmosphere remains intact, that the planet avoids sterilizing flares, or that its climate settles into something biologically stable. Around red dwarfs, those extra questions become central almost immediately. Even before the issue of stellar activity arises in full, the closeness alone begins to reshape the world. Gravity is stronger at shorter distances, and the difference in gravitational pull across the planet becomes more important. Over time, this can alter rotation, interior heating, and orbital behavior. A planet that began with a more Earth-like spin may be drawn toward a state in which one hemisphere faces the star continually, while the other faces permanent night. That possibility does not make habitability impossible, but it means a red dwarf world is unlikely to resemble the balanced daily cycle that shaped Earth's surface environments. The familiar picture of sunrise and sunset across a global climate system can be replaced by a more extreme arrangement, with a bright side under constant illumination and a dark side under continual cold. The habitable zone, then, is not only narrow in distance, it is narrow in the sense that favourable temperature must coexist with a suite of destabilising influences. That is what makes these systems so compelling. They are not simple versions of the solar system repeated many times. They are different planetary arrangements with different tensions built into them. What matters here is that the very quality that gives red dwarfs such long futures, their low, efficient output, also pushes potentially habitable worlds into far more intimate relationships with the star. A planet cannot enjoy the red dwarf's longevity from afar. It must come close enough to collect the modest stream of energy the star provides. In doing so, it enters a region where distance no longer acts as a protective buffer. This has consequences for climate from the beginning. On Earth, the broad distribution of sunlight across a rotating globe, combined with atmosphere and oceans, produces circulation patterns that moderate extremes. Around a red dwarf, especially for a tidally locked world, the incoming energy may be concentrated in a way that creates sharp thermal gradients from one hemisphere to the other. Atmospheric and oceanic transport may still redistribute heat, and under the right conditions this could preserve broad habitable regions rather than a single narrow band. But such stability depends on the planet having enough atmosphere, enough water, and a sufficiently robust climate system to avoid collapse into either frozen night-side trapping or runaway dayside heating. The zone of possible habitability therefore becomes a zone of climate negotiation, where multiple planetary properties must cooperate. This is one reason the search for red dwarf life has grown more sophisticated over time. The early hope was simple and powerful, because red dwarfs are common and long-lived, and because many appear to host rocky planets. The galaxy might be filled with potentially habitable worlds. That hope has not disappeared, but it has become more careful. The question is no longer only how many planets sit at the right distance. The deeper question is how many of those planets can remain temperate under close orbit conditions for billions or trillions of years. A world may begin with water and still lose it. It may begin with an atmosphere and still erode it away. It may occupy the nominal habitable zone and still end up more like Venus than Earth. Not because the zone was wrongly defined, but because distance alone never captured the whole problem. Red dwarfs make that limitation especially clear. They force astronomy to distinguish between formal habitability and lived habitability, between receiving enough energy for liquid water in principle and sustaining a planetary environment where water, air, chemistry, and climate endure together. This distinction matters because red dwarf planets are likely to be among the most numerous rocky worlds available for future study. They are nearby, they are detectable. Some orbit in compact multi-planet systems where several worlds sit close to one another and close to the star. Such systems are scientifically rich because they allow comparisons under shared stellar conditions. A single red dwarf can host several rocky planets at different distances, each one receiving a different dose of energy, each one offering a slightly different climate experiment. In those arrangements, the habitable zone becomes not just a theoretical ring, but a testable region, a place where astronomers can compare worlds that may diverge sharply despite orbiting the same star. One may be stripped and dry, another may hold a dense atmosphere, another may lie just outside the range where surface water can persist. Together they reveal how sensitive red dwarf planets are to position and planetary history. This is part of why the subject carries such quiet weight. Red dwarfs dominate the stellar population, and their habitable zones may contain vast numbers of rocky bodies, but the conditions inside those zones are far more demanding than the phrase habitable suggests. Warmth exists there, but so does compression. Opportunity exists there, but only close to forces that can undo it. Even the colour of the starlight changes the story. A planet orbiting a red dwarf receives a spectrum shifted toward redder wavelengths, with less of the visible light familiar from Earth and more infrared energy. That altered light environment affects atmospheric chemistry, surface reflection, and potentially photosynthesis if life were to arise. The star's dimness does not simply reduce brightness, it changes the quality of the planetary day. Such worlds may live beneath deeper crimson skies or dimmer illumination filtered through clouds and gases under unfamiliar spectral conditions. They are not lesser Earths placed closer to a smaller sun. They are worlds with their own physical logic, their own climate constraints, and perhaps their own biological possibilities if biology can take hold there at all. By the end of this first approach to red dwarf planets, the habitable zone no longer looks like a safe ring waiting to be filled. It looks like a narrow region where promise and vulnerability occupy the same space. A red dwarf can offer a world astonishing amounts of time, but only if that world survives the intimacy the arrangement demands. The distance is small. The stakes of that smallness are not. On a planet orbiting close to a red dwarf, the sky may stop moving in the familiar way long before life has a chance to judge the arrangement. Because the habitable zone lies so near the star, gravitational forces can gradually reshape the planet's rotation until one hemisphere remains turned toward the light, while the other remains in darkness. This state, known as tidal locking, is one of the most discussed features of red dwarf worlds because it changes something deeper than temperature alone. It changes the structure of day and night. On Earth, rotation breaks sunlight into a cycle. Warmth arrives, recedes, and returns. Winds, clouds, and surface temperatures respond to that rhythm. On a tidally locked world, the rhythm may be replaced by permanence. The star hangs nearly fixed above one region of the surface. Another region never sees it at all. Between them lies a shifting boundary of twilight, a planetary margin where the contrast between heat and cold may become the central fact of the environment. At first this sounds fatal to habitability, and for a long time it was treated that way. A permanently illuminated hemisphere seems destined to overheat, while the dark hemisphere seems likely to freeze its atmosphere onto the ground. Yet the deeper question is not whether the geometry is extreme. It is whether the planet can move enough heat to soften that extremity. If a world has a substantial atmosphere, or large oceans, or both, then circulation can carry energy away from the day side and spread it across the globe. Winds may rise from the hot substellar region and flow outward. Air cooled on the night side may sink and return. Ocean currents, if liquid water remains abundant, can transport warmth through slower but powerful pathways. In that case, tidal locking becomes less a death sentence than a climate problem of unusual shape. The contrast remains severe, but not necessarily absolute. The day side may be cloud-covered rather than scorched. The night side may be cold without becoming airless. Some models suggest that habitable regions could survive over broad belts or even across large fractions of such planets if the atmosphere is thick enough and the water cycle strong enough. What matters here is that tidal locking does not end the story, but it does make the story harder. A red dwarf world must work against a form of climatic asymmetry that Earth never faced at the same scale. Even where temperatures remain moderate overall, the geography of survival may be uneven, concentrated not across a rotating globe but along favoured regions where circulation and radiation come into temporary balance. The old image of a habitable planet as a broadly Earth-like sphere becomes less secure here. A habitable red dwarf world may instead be a place of permanent hemispheres, fixed weather systems, and environmental gradients so large that crossing the surface could feel like travelling between planets. That alone would make such worlds unusual. But tidal locking is only the first pressure. The star itself introduces a second, often more serious one. Red dwarfs are small, yet many are magnetically active in ways that can make their immediate surroundings harsh. The reason lies partly in their internal structure. In many red dwarfs, convection reaches through most or all of the star, and when convection interacts with rotation and magnetic fields, it can generate strong magnetic activity. That activity appears at the surface as dark star spots and in the surrounding atmosphere as sudden flares. bursts of energy released when twisted magnetic fields reconnect. The scale of those flares can be startling. Because the star is faint to begin with, even a modest increase can change its apparent brightness sharply. More important than the visible change is the radiation that accompanies it. Flares can produce intense ultraviolet light, X-rays, and streams of energetic particles for a planet orbiting close by. There is little distance available to dilute the effect. The same proximity that keeps water from freezing may also place the atmosphere under repeated assault. This is where the red dwarf problem becomes genuinely severe. A world can adapt to constant geometry more easily than to repeated atmospheric damage. High-energy radiation can break apart molecules in the upper atmosphere, alter chemical pathways, and heat the outer layers enough that gases escape to space more readily. Energetic particles guided by stellar magnetic fields can erode the atmosphere further, especially if the planet lacks a strong magnetic shield of its own. Over long spans, this process can strip a world of much of its protective air and much of its water, leaving behind a dry surface exposed to radiation and unable to regulate temperature effectively, even if the habitable zone places the planet at the right average distance for liquid water. That advantage may be undone if the atmosphere cannot survive the star's activity. The danger is not confined to rare giant events. Many red dwarfs, especially when young, flare often. Some show bursts so frequently that the planetary environment may spend much of its time recovering from one disturbance only to encounter the next. A planet with a robust atmosphere and magnetic field may endure this punishment better than a thin, unprotected one. But endurance is not guaranteed. The cumulative effect of thousands or millions of energetic episodes matters more than any single dramatic burst. Atmospheric escape, photochemical disruption, and surface radiation exposure can build slowly into irreversible change. There is also a quieter form of stellar variability that complicates the picture. Red dwarfs can be heavily marked by star spots, dark magnetic regions that reduce the amount of light emitted from parts of the surface. If such spots cover a large enough fraction of the star, the total energy output can dip significantly for extended periods. On a world already living close to the minimum energy needed for liquid surface water, this matters. A prolonged reduction in incoming light can cool the climate, expand ice cover, and shift atmospheric circulation. If the planet's climate system is fragile, such dimming episodes might push it toward global freezing. The details depend on the composition of the atmosphere, the amount of greenhouse warming available, the presence of oceans, and the speed with which heat can be redistributed from one hemisphere to another. But the broad point remains: red dwarfs do not always provide steady, unchanging illumination. Some offer climates interrupted by stellar moods, not violent enough to strip the world at once, perhaps, but sufficient to test whether the planet can retain stability through repeated swings in energy input. These two forms of instability, sudden flares and slower spot-driven dimming, pull in opposite directions. One threatens overheating, radiation damage, and atmospheric loss. The other threatens cooling and ice expansion. A world in the habitable zone may therefore face not a single environmental pressure but alternating ones, each working through a different timescale. Stability under such conditions is possible in principle, but it would likely depend on a rare balance of circumstances. The planet may need a dense atmosphere to smooth temperature contrasts, a strong magnetic field to reduce erosion, substantial water inventories to buffer climate shifts, and enough geological activity to recycle gases and sustain long-term atmospheric renewal. Lose one of those supports, and the environment becomes harder to preserve. Lose several, and the star's longevity becomes almost irrelevant, because the planet may be rendered sterile long before the red dwarf settles into a quieter maturity. That last point introduces an important complication. Red dwarfs can calm with age. Many are most active in youth, when rotation is faster and magnetic behavior more intense. Over time, some slow down and become less violent. In principle, this could create a better long-term environment later on. But by then, much damage may already have been done. A planet that spent its early history under heavy flare bombardment or elevated stellar luminosity may have lost its surface water before any calmer era began. An atmosphere once stripped is not easily replaced unless the planet has deep internal reserves and active geology. So the question is not simply whether a red dwarf is calm now, it is whether the planet survived the star's earlier restlessness well enough to benefit from the calmer future. This makes the path to habitability around red dwarfs unusually selective. The right distance is only the first filter. After that comes rotational state, atmospheric retention, magnetic protection, climate buffering, and resilience across a long active youth. Any world that remains temperate after all that would be a significant success of planetary persistence. Yet none of this removes the possibility altogether. It narrows it. A red dwarf planet may still sustain broad habitability if its atmosphere is thick, its water abundant, its circulation vigorous, and its star moderate rather than extreme. The data does not end the possibility, it changes the shape of it. Life around red dwarfs must be imagined not in the easy centre of a stable system, but in the negotiated space between close orbit physics and stellar volatility. The sky may be locked, the star may be restless, the atmosphere may stand under constant test. If a living world survives there, it does so not because the environment is gentle, but because it has found a way to remain whole under repeated pressure. The light reaching a habitable planet around a red dwarf would not feel like sunlight reduced. It would be filtered through a different stellar character from the beginning, shaped by a cooler surface, a redder spectrum, and a sky in which energy arrives with a different balance of wavelengths than life on Earth has ever known. This matters because life does not merely require warmth, it requires an environment in which chemistry can persist, water can remain available, and energy can be harvested in stable enough ways for complexity to grow. Around red dwarfs, all of those conditions may still be possible, but they would likely take forms less familiar than the Earth-centered picture habitability once implied. The interest in these worlds does not come from the hope that they are simple copies of Earth orbiting smaller stars. It comes from the possibility that biology may be more flexible than Earth alone can demonstrate, and that environments once dismissed as too strange may still offer long windows of opportunity if the right planetary conditions are present. This is why oceans matter so much in discussions of red dwarf life. On a world orbiting close to one of these stars, especially a tidally locked world, water may be one of the strongest stabilizing forces available. Large bodies of liquid water can absorb heat on the permanent day side, transport it through currents, and release it more slowly elsewhere, reducing the contrast between the hot hemisphere and the cold one. An ocean does not eliminate the asymmetry built into the orbit, but it can soften it. It can turn a world that might otherwise divide into fire and frost into one where broad belts of temperate conditions remain possible. Water also drives weather, cloud formation, and the cycling of gases between surface and atmosphere, all of which can help regulate climate across long periods. A red dwarf planet with deep oceans might therefore be more resilient than a dry one, not because water solves every problem, but because it gives the climate more ways to redistribute energy before extremes become final. The same logic applies to atmospheres. A thick atmosphere is not merely a blanket that keeps a world warm, it is a transport system, a chemical medium, and a buffer against sudden change. On a tidally locked world, Air currents can move heat away from the substellar point and carry it into darker regions. On a world subject to changing stellar output, a substantial atmosphere may prevent every fluctuation from reaching the surface in full force. The atmosphere also determines whether water remains liquid, whether harmful radiation reaches the ground, and whether essential molecules can cycle through stable pathways. Around red dwarfs, atmospheric survival is one of the great uncertainties, but where it does survive, it may create environments more forgiving than simple orbital geometry suggests. In some climate models, even worlds with permanent day and night hemispheres can maintain habitable surface regions if their air is thick enough and their circulation strong enough. That does not guarantee biology. It only restores the possibility of it. But that restoration matters because it shifts the question from impossible in principle to demanding in detail. Once that shift happens, the range of plausible living worlds expands beyond the narrow image of an Earth twin. A red dwarf planet might support life under a dense atmosphere richer in greenhouse gases than Earth's, or beneath a more extensive cloud deck reflecting part of the incoming stellar energy, or across an ocean-covered surface with only scattered land. The climate could be dimmer, redder, and more spatially uneven than Earth's, while still offering stable chemical niches. Photosynthesis, if it emerged, would likely face a different energy environment because red dwarfs emit much of their radiation at longer wavelengths. On Earth, photosynthetic pigments attune to the spectrum of the sun, especially the visible range. Around a red dwarf, biology might favour different pigments, different metabolic pathways, or different ecological balances between light-driven and chemically driven life. The idea is speculative, but the basic principle is sound. Life adapts to available energy. If the energy landscape changes, the machinery of life may change with it. This opens a quieter and more interesting possibility than simple resemblance. A living red dwarf world might be biologically active without looking Earth-like at all. Its dominant organisms could grow under a dim crimson daylight. Its most productive habitats might lie near coastlines of the twilight zone or in shallow seas where heat, circulation, and chemistry meet. Its atmosphere might carry biosignatures unfamiliar in proportion, even if they arise from recognizable processes. The deeper question is not whether such life would mirror the terrestrial pattern, but whether a red dwarf environment can remain stable long enough for any pattern of life to take root and elaborate itself. Here the long lifespan of the star becomes newly important. Even if the path to early habitability is difficult, a successful world around a moderate red dwarf may have access to durations almost beyond comparison. Life on Earth required hundreds of millions of years to become firmly established, and billions more to produce complex ecosystems. A red dwarf can offer not just such durations, but vastly more, provided the world survives the star's early volatility. This means the reward for planetary resilience may be immense. A biosphere that makes it through the difficult beginning could, in principle, continue under a relatively stable source of energy for spans so long that evolutionary time acquires an entirely different scale. That possibility is one reason red dwarfs remain central to the search for life, despite all their hazards. They do not merely offer many planets, they offer many chances extended over extraordinary lengths of time. The range of candidate worlds also appears wider than the first habitable zone discussion suggested. Rocky planets near Earth's size are important because they are the most obvious analogues for surface water and atmosphere. But they may not be the only useful settings. Super-Earths, rocky planets more massive than Earth, could retain thicker atmospheres and stronger internal heat budgets, which might support long-term tectonic or volcanic recycling of gases. That could help rebuild or preserve an atmosphere after periods of stellar stress. Greater gravity could also reduce the rate at which lighter gases escape to space, though it might come with other trade-offs in surface conditions and geophysics. The label Super Earth does not imply a better Earth. It describes mass, not habitability. Some such planets may be crushingly dense, shrouded in heavy atmospheres, or geologically hostile, but as a class, they widen the field of possibility by showing that Earth size is not the only planetary scale at which rocky environments may remain active and chemically complex around a red dwarf. Large moons may widen it further. A giant planet orbiting within or near the habitable zone of a red dwarf could host moons with substantial water, atmospheres, and internal heating. In the solar system, moons such as Europa and Enceladus show how tidal energy can keep water liquid beneath ice far from the sun. Around a red dwarf, a large moon receiving both stellar energy and tidal heating could become an especially interesting hybrid case. It might preserve subsurface oceans even if surface conditions fluctuate. If it possessed a thick enough atmosphere, it might even sustain temperate surface regions under some circumstances. Such worlds would be dynamically complex, shaped by the gravity of both planet and star. But complexity is not always a barrier to habitability. Sometimes it is the source of persistence. Internal heating can prevent global freezing. Gravitational cycling can sustain long-term activity. A moon or super-Earth in a red dwarf system might therefore remain habitable not by resembling Earth's exact balance, but by combining multiple energy sources and buffering mechanisms. This broader view changes how alien life is imagined around small stars. The most plausible living world may not be an exact terrestrial copy with blue skies, moderate continents, and familiar seasons. It may be an ocean planet with permanent cloud formations under red light. It may be a large rocky world with a dense, stable atmosphere and strong heat transport. It may be a moon orbiting a gas giant, where tidal flexing supports hidden seas beneath an illuminated surface climate. It may even be a world where surface life is limited but subsurface ecosystems flourish for immense spans, protected by rock, water, and chemistry from the harsher conditions above. The question is no longer whether red dwarfs can host Earth-like life in the narrowest sense. The question is whether they can host persistent living systems in forms broad enough to include unfamiliar planets, unfamiliar ecologies, and unfamiliar balances between surface and interior. That distinction matters because Earth itself offers only one example of life, and one example is not a reliable measure of all that biology may tolerate. Astronomy can define physical limits. Planetary science can describe possible environments. But between those constraints lies a large territory of biological uncertainty. Red dwarfs sit directly inside that uncertainty because they create worlds that are neither clearly welcoming nor clearly sterile. They are conditional worlds. Their climates may depend on thick atmospheres, deep oceans, reflective clouds, magnetic protection, and geological renewal all working together. Where that cooperation fails, the result may be desolation. Where it holds, the result may be extraordinary longevity. That balance is what keeps the search open. There may be billions of potentially temperate planets around red dwarfs in the Milky Way alone, but the word potentially carries real weight. It does not promise forests, oceans full of life, or civilizations beneath crimson suns. It marks a boundary between what physics allows and what history may yet produce. Still, even that boundary is remarkable. The most common stars in the galaxy may host not just rocky worlds, but whole categories of worlds whose habitability depends on climate systems unlike Earth's and timescales far longer than Earth will ever possess. If life can survive there, it may do so under conditions less familiar but more durable, in environments where the light is softer, the star is smaller, and the future is measured not in billions alone but in stretches of time so great that biology itself could become something far older and stranger than anything the present world has known. The possibility remains unsettled. Everything observed so far can be arranged into plausible pathways, but not yet into a settled picture, and that difference is what makes red dwarf life more than a question of location. It becomes a question of endurance, adaptation, and whether living worlds can remain alive under red light long enough to inherit the longest ages of the stars. Long before the sun reaches its final collapse, Earth begins to lose the conditions that make complex life possible. The first decisive change is not explosion or sudden darkness, but heat added slowly enough to seem harmless at first. As the sun ages on the main sequence, it grows brighter in a gradual, relentless way. That extra luminosity alters the climate balance of Earth over immense spans, increasing evaporation, intensifying weathering, and eventually pushing the planet toward a state where oceans retreat and the carbon cycle that now stabilizes climate can no longer function in the same way. The timescale is vast by human standards, but short compared with the lifespan of a red dwarf. In roughly 1 billion years, Earth may already be too warm for complex surface ecosystems to endure comfortably. Much later, the sun will swell into a red giant and transform the inner solar system far more violently, but for any civilization capable of looking ahead, the real warning arrives much earlier. The problem is not simply that the sun will die. The problem is that habitable time on Earth is limited, and limited in a universe where other stars may continue offering usable energy for durations almost beyond comparison. That is where red dwarfs begin to matter, not just as astronomical objects, but as possible long-term refuges for intelligence, technology, and continuity. Their appeal does not come from comfort alone. It comes from duration. A civilization hoping to survive for millions, billions, or even far longer years cannot think only in terms of immediate resemblance to Earth. It must think in terms of available futures. A red dwarf with the right planetary system may offer one of the longest stable energy environments the cosmos can produce. The phrase "the right planetary system" carries most of the difficulty. By now the hazards are clear. Many red dwarfs are too active in youth. Many close-in planets may lose their atmospheres or water before long-term stability becomes possible. Some worlds may be tidally locked in ways that make broad habitability difficult. Yet if even a small fraction of red dwarfs host planets or moons that preserve oceans, atmospheres, and moderate climates across great spans, then the number of viable destinations may still be enormous simply because red dwarfs themselves are so abundant. Even a narrow window multiplied across the galaxy becomes a significant landscape of possibility. This is why red dwarfs occupy such an unusual place in long-range thinking about survival. They are not the easiest stars to live beside, but they may be the most consequential once time itself becomes the main constraint. For a civilization born around a sun-like star, that shift in priority would be profound. Early astronomy might favor brighter, more familiar systems, places where day length, light spectrum, and orbital spacing resemble what life already knows. But over deeper time, the question changes. Similarity begins to matter less than persistence. A red dwarf need not offer an Earth duplicate to be valuable. It need only offer a stable enough world, or network of worlds, where atmosphere, water, chemistry, and energy remain accessible for ages that far outlast anything available around a star like the Sun. In that sense, the red dwarf becomes less a second choice than a strategic one. It is the kind of star a civilization may approach not first, but eventually, when the scale of planning extends beyond a homeworld and beyond a home era. The Milky Way likely contains billions of rocky planets around red dwarfs, and among them there may be many systems old enough to have settled into quieter conditions after active youth. Some may host worlds that formed with deep water reserves. Some may include super-Earths able to hold thick atmospheres and maintain internal heat. Some may contain large moons orbiting giant planets in stable configurations. Others may simply have been lucky, orbiting stars whose activity remained moderate enough for atmospheric loss never to become catastrophic. Any one of these cases, if real, would be more than another exoplanet. It would be a possible platform for very long continuity. A civilization thinking across geological timescales might value such a place less for its scenery than for its patience. Around a red dwarf, the future does not close quickly, it remains open. That openness changes the meaning of settlement as well. Under a short-lived star, even a successful world carries an approaching deadline built into its sky. Under a red dwarf, the available horizon stretches outward so far that ordinary political or historical terms begin to feel small. A stable planetary environment could support not merely the rise and fall of cultures, but long sequences of biological and technological change, layered across durations that exceed the entire past of Earth many times over. Continents might shift, species might change beyond recognition. Languages, forms of consciousness, or even the definition of civilization might drift into unfamiliar territory. Yet the star would still remain in its long, efficient central phase, providing the steady low output that makes such continuity possible. This is part of what makes red dwarfs feel less like local stars and more like infrastructure for the far future. They are not dramatic, but they are durable enough to hold open the possibility of history on scales no human society has ever needed to imagine. That is equally true if the future belongs not to biological humanity in its present form, but to descendants altered by engineering, adaptation, or migration. A species expanding through space would not necessarily require a perfect terrestrial environment at every destination. It might build habitats in orbit, beneath ice, underground, or within engineered atmospheres. It might alter worlds to increase cloud cover, redistribute heat, or preserve volatiles. It might choose planets not because they are naturally comfortable, but because they are workable under a star that will remain available for trillions of years. From that perspective, a red dwarf system becomes a long-term energy source around which many forms of habitation could be arranged. A marginal natural world might still become a durable home if technology bridges the remaining gap. The question is then no longer whether red dwarfs provide ideal planets by themselves, but whether they provide systems within which a sufficiently advanced civilization can construct lasting ecological and social continuity. Their low luminosity becomes an inconvenience to manage. Their longevity becomes the decisive advantage. There is also a civilizational logic to moving slowly outward through time. The nearest stars to the Sun are often red dwarfs. That means the earliest interstellar migrations, if they ever occur, may encounter red dwarf systems not as remote final sanctuaries, but as the first practical frontier. Some may prove barren or hostile, others may contain airless rocks, stripped atmospheres, or worlds trapped in deep tidal imbalance. But some may also contain temperate planets, water-rich moons, or at least raw materials and stable energy conditions sufficient for artificial settlement. If so, then red dwarfs may become woven into the expansion path of any long-lived spacefaring lineage simply because they are nearby, numerous, and difficult to avoid. Over time, what begins as a matter of local exploration could become a deeper migration pattern, with red dwarf systems gradually forming one of the main inhabited archipelagos of the galaxy. This possibility is speculative, but it follows naturally from the statistics of stars. A civilization expanding through the Milky Way would not mainly encounter bright sun-like systems, it would mainly encounter red dwarfs. Their abundance ensures that the future geography of settlement, if settlement comes, will likely be structured around them whether by choice or by repetition. And if life exists elsewhere already, the same reasoning applies in reverse. Alien civilizations born around more massive stars may also face deadlines. Alien biospheres may also need long-term stable energy sources. A moderate red dwarf with a surviving habitable world would be valuable to them for the same reason it would be valuable to any civilization, not because it is easy, but because it lasts. This makes red dwarfs relevant to the search for intelligence as well as the search for simple life. A world orbiting one of these stars may have had more time than Earth has yet enjoyed, perhaps much more, to pass from chemistry into biology, from biology into complexity, and from complexity into technology, provided the early environment was stable enough for that chain to begin. The long life of the star does not guarantee such an outcome, but it removes one of the strictest limits. It leaves room for patient evolution and for long cultural continuities once intelligence appears. In that sense, red dwarfs may not only host life, they may host the kinds of futures in which life has time to become old. None of this makes them gentle. The earlier difficulties remain. Young red dwarfs may strip worlds bare. Close habitable zones still create hard constraints. Tidal locking, atmospheric erosion, and spectral differences still shape every possible refuge. But a refuge does not have to be easy. It has to be survivable, stable, and durable enough to justify the effort of reaching it. That is the standard red dwarfs may yet meet. Their importance lies not in resembling the cradle where a species began, but in offering somewhere the long middle of cosmic history can continue after that cradle fails. Earth is not lost now. The sun is not near its end now. But on the longest scales that matter to astronomy, departure is built into the future of every world around a star like ours. Red dwarfs enter that picture as the opposite of urgency. They wait. They persist in the dark among brighter, shorter-lived stars. They offer less light, fewer comforts, and more complications. Yet they also offer something no luminous giant can match and no sun-like star can sustain for so long a chance to build continuity under a source of energy that seems almost unwilling to end. If one suitable world exists around a moderate red dwarf, it is already a remarkable prize. If many exist, then the galaxy may contain not just scattered habitable planets, but an immense reserve of possible futures, held in orbit around the faintest stars and preserved there for timescales so long that even the history of Earth begins to look like an opening chapter. The end of a red dwarf is not expected to arrive with grandeur. After such a long career of restraint, its final transformation is shaped by the same principle that defined its life: nothing happens quickly, and very little is wasted. A star like the Sun grows old by exhausting hydrogen in its core, swelling outward into a red giant and entering a visibly dramatic change of form. A red dwarf follows a quieter path because it mixes its material so efficiently. It does not build up the same isolated, exhausted core while leaving large outer layers untouched. It uses its hydrogen more completely, and that changes how old age unfolds. The star does not need to expand into a giant to keep fusion going in new regions. Instead, over immense spans, the balance of hydrogen and helium throughout the interior shifts gradually. The star becomes denser in composition, hotter in its active regions, and somewhat brighter than it was in youth. This is one of the subtle reversals red dwarfs introduce into stellar evolution. They begin dim and cool, but the road toward their end is expected to make them bluer and more luminous for a time. Not because they become large and unstable, but because they continue burning with increasing efficiency as the remaining hydrogen fraction declines. In theory, that late stage produces what astronomers call a blue dwarf, not a separate kind of object born in nature today, but a future phase of a once red dwarf star that has aged far beyond anything the universe has yet had time to create. No blue dwarfs are known, because the universe is still far too young. The phrase belongs to prediction, not observation. Yet the prediction follows naturally from the physics of stars that remain fully mixed for most of their lives. A red dwarf does not move toward its end by outward display, it moves inward through a slow change in composition that gradually shifts the character of the star's light. That transition is important because it marks the point where long endurance begins to encounter real limitation. Even the most patient stellar engine cannot fuse hydrogen forever. Eventually, after trillions of years, enough of that fuel is gone that the star can no longer sustain the process in the way it once did. Its long stability starts to break. The final hydrogen burning becomes concentrated under changed internal conditions. The star is no longer the same dim, quiet object it once was, even if its outer scale remains modest. It has grown older not by swelling into spectacle, but by refining itself into a hotter, more exhausted state. This is the nearest red dwarfs come to a last brightening, and even that is not dramatic by the standards of more massive stars. There is no supernova waiting here, no immense pulse of outer layers cast across space. Small stars do not die with violence because they never build the internal architecture required for violent ends. They remain below the thresholds needed to ignite heavier fusion stages. Carbon does not become their next great fuel. Oxygen and silicon do not follow. Their cores never march toward iron, and so they never face the catastrophic collapse that makes a massive star explode. A red dwarf's entire life is built around hydrogen, and once hydrogen is effectively gone, the options narrow rapidly. The star contracts. Its active burning ceases. What remains is the compact remnant of a very long life, a white dwarf. This remnant would differ somewhat in detail from the white dwarfs produced by stars like the Sun, because the path to get there is not the same. A Sun-like star sheds much of its outer material after giant phases and leaves behind a carbon-oxygen white dwarf. A very low-mass red dwarf, by contrast, is expected to end as a helium white dwarf, because its core never reaches the conditions needed to fuse helium into heavier elements. The distinction matters because it shows how thoroughly the star remained confined to its original fuel. After trillions of years, after using far more of its hydrogen than a larger star ever could, it still never crossed into the more advanced nuclear stages that make stellar death spectacular elsewhere. It simply ends with a compact, hot remnant, supported not by ongoing fusion but by the quantum mechanical pressure of densely packed matter. That remnant, though Earth-sized in scale, contains a large fraction of the star's original mass compressed into a volume so small that ordinary intuition becomes useless. The white dwarf is no longer a true living star in the old sense. It is not generating fresh energy from nuclear reactions. It shines because it is still hot, because the stored heat of its compressed matter leaks outward slowly into space. For a long time, that is enough to make it a visible object. But the white dwarf is only cooling now. Its history has changed direction. During the red dwarf phase, time meant continuation. During the white dwarf phase, time means decline. Even so, decline remains extraordinarily slow. White dwarfs cool over vast periods, radiating away their heat with no internal source to replace it. The smallest red dwarfs will enter this stage only in the remote future, long after every star more massive than they are has already finished its own active life. By then, the universe will be a very different place. Star formation will have dwindled. Many galaxies will have aged into quieter populations. The bright, crowded stellar eras that shape the early and middle history of the cosmos will already be gone. Against that darkened background, a newly formed white dwarf from an ancient red dwarf will still begin hot, compact, and faintly luminous, like an ember produced at the end of the longest burning fire. But embers cool. over further unimaginable stretches of time, the white dwarf loses more and more of its thermal energy. Its light weakens, its temperature falls, its glow passes from white through redder and dimmer stages until, in theory, it becomes a black dwarf, a remnant so cooled that it emits essentially no visible light at all. Like blue dwarfs, black dwarfs do not yet exist in the observable universe, not because the idea is doubtful, but because the timescale is too long. The universe has not lasted long enough for any white dwarf to cool that far. Black dwarfs belong to a future beyond all present observation, a stage of cosmic aging still entirely ahead. There is something fitting in that. Red dwarfs begin their story as stars whose full lifetimes exceed the age of the universe, and even after they die, their remnants continue cooling on timescales the current cosmos has not yet reached. Their endings are not merely late, they are deferred beyond every directly witnessed stellar conclusion of their kind. This makes the death of a red dwarf both conceptually simple and emotionally strange. The sequence itself is not complicated. A small, fully convective hydrogen-burning star ages very slowly, brightens somewhat as its composition changes, passes through a theoretical blue dwarf phase, ends fusion, and becomes a compact white dwarf remnant that cools toward blackness. But the timing of that sequence is so extended that it hardly feels like an ending in the ordinary sense. It feels more like the final settling of one of the universe's last reliable engines. This is why the red dwarf's death carries weight out of proportion to its spectacle. If a massive star explodes, the event is brilliant, but it belongs to a cosmos still full of other active stars. When the last red dwarfs die, the context is entirely different. By then, starlight itself will be scarce. The white dwarf left behind will not be one remnant among many bright neighbours. It will be part of the long diminishing residue of the stelliferous age, one of the final traces left after ordinary starshine has nearly run its course. The passage from red dwarf to white dwarf is therefore not only a local transformation, it is part of the universe losing one of its final durable forms of organised light, and yet even here, the manner of ending remains restrained. Red dwarfs do not burn out in anger. They do not tear themselves apart. They fade into compactness and then into cooling. The late universe inherits not explosions from them, but relics. Small, dense, slowly darkening objects remain where patient stars once stood. Their matter persists. Their heat leaks away. Their last distinction is not intensity, but duration. That long duration also emphasizes an important limit. It is tempting to treat red dwarfs as nearly eternal, because their lives are so much longer than anything familiar. But nearly eternal is not eternal. Even the most efficient star built from ordinary matter runs out of usable fuel eventually. Even a white dwarf's stored heat is finite. Even a black dwarf, once it exists, is only the cold aftermath of processes that are no longer active. Red dwarfs are the great conservers of cosmic time, but they do not escape the rule that all structured energy release has an end. They simply postpone that end so far into the future that every brighter star appears brief by comparison. That is what gives their death its unusual dignity. A red dwarf has no spectacular final act because its whole existence has been an answer to extravagance. It begins near the minimum threshold of starlight, burns with discipline for trillions of years, and then leaves the stage by shrinking into a remnant rather than swelling into ruin. The final transformation is not a violation of its nature, it is the completion of it. What remains afterward is a white dwarf cooling in deep time, and beyond that, eventually, a black dwarf lost in darkness. The structure is suggestive, the theory is strong, and the physical logic is clear. What is still missing is direct witness. because the universe has not yet lived long enough to show the ending of its faintest, most enduring stars. There will come a time when a galaxy like the Milky Way no longer looks anything like the one that hangs above Earth today. The bright blue stars will be gone first, because they are always gone first, having spent their energy in brief, extravagant lives. Sun-like stars will follow on much longer schedules, swelling, shedding, collapsing into white dwarfs, and leaving behind systems altered beyond recognition. Even many stars smaller than the Sun will eventually finish their steady hydrogen-burning lives. The great visible architecture of the present sky, with its mixture of youthful brilliance and moderate stellar age, belongs to a temporary interval in cosmic history. It feels permanent only because human beings exist inside it. From the perspective of deep time, it is a transitional brightness, a middle chapter between the violent early universe and the far quieter ages still to come. In those later eras, red dwarfs do not merely survive. They increasingly define what starlight means. Their importance grows not because they change into something more spectacular, but because everything more extravagant has already fallen away. This is the final reversal built into their nature. The faintest ordinary stars become, by endurance alone, the principal lights of the late universe. To understand that future, it helps to widen the scale beyond individual stellar systems. Galaxies do not go on forming stars forever at the same rate. Star formation depends on cold gas, and that gas is gradually consumed, heated, expelled, or locked into objects that no longer participate easily in building new stars. Over billions of years, the supply changes. In many galaxies, the most active era of star birth already lies in the past. The Milky Way still forms stars, but not with the urgency of its youth. Eventually, over immensely longer spans, the production of new stars will dwindle further. The universe will not suddenly turn dark in one moment. It will simply become less generative. Fewer clouds will collapse. Fewer fresh stars will ignite. The stellar population will age in place. Under those conditions, what remains luminous depends less on new creation and more on which stars were built to last. Massive stars are of no use in such a future. They are too brief. Even stars like the Sun are only temporary reservoirs of organized light. Red dwarfs, by contrast, inherit the long decline of cosmic star formation almost effortlessly. They do not need replenishment. Their own lifetimes are already vast enough to bridge eras that would exhaust every brighter class of ordinary star. In the far future, then, the continued existence of starlight will depend heavily on what red dwarfs are still doing, and for an astonishing length of time they will still be there, continuing their slow fusion under conditions that will make the rest of the stellar universe seem spent. This has a profound effect on the emotional geometry of the cosmos. The present universe is crowded with mixed ages and mixed scales of stellar life. There are giant stars still burning, white dwarfs already cooling, neutron stars left behind by ancient explosions, and new stars still being born in molecular clouds. It is a universe of overlap. The far future shaped by red dwarfs is very different. It becomes a universe of residue and persistence, where the main surviving ordinary stars are not bright landmarks but quiet engines of exceptional thrift. A galaxy in that era would still contain many remnants of past brilliance. But the active, fusion-powered lights would be increasingly concentrated in the smallest stars. Whole regions might be illuminated only sparsely, with enormous distances between functioning suns. The sky from any inhabited world, if inhabited worlds remain, would not resemble a richly layered stellar field. It would be thinner, dimmer, and older, with red dwarfs serving as the principal anchors of warmth against a background increasingly dominated by cold relics and dark intervals. There is an important distinction here between absolute darkness and relative darkness. The universe does not lose light all at once, and it does not become empty simply because the bright stars are gone. White dwarfs still glow for long periods. Neutron stars and black holes persist. Stellar remnants continue to shape gravity, motion, and occasionally the fates of nearby matter. But the age of abundant ordinary starlight narrows steadily, and red dwarfs extend it more than any other stars can. They are the last widespread class still performing the old stellar work of turning hydrogen into sustained outward light over truly immense spans. Even after the galaxies have grown quieter and more settled, even after the flamboyant forms of stellar youth have become purely historical, red dwarfs preserve a diluted but real continuation of the luminous universe. This is why they matter so much to any long view of cosmic habitability. If warmth, chemical disequilibrium, and long-term environmental stability remain possible anywhere in the late stelliferous era, red dwarfs are among the likeliest places to find them. A moderate red dwarf with a surviving planet, moon, or engineered habitat would not merely be another living system in a galaxy of stars. It might be part of one of the last broadly available categories of long-duration refuge. The rest of the galaxy would still contain matter in abundance, but usable stellar energy would become a more selective resource. Under those conditions, the difference between a star that lives for billions of years and a star that lives for trillions becomes civilizational, biological, and perhaps even philosophical. It marks the difference between a future with many openings and one where openings are growing rare. Red dwarfs do not prevent the decline of the luminous universe. They slow its disappearance. That slowing may be enough to support astonishing continuities. A biosphere that survived around a calm red dwarf could persist through stretches of time so much longer than Earth's future that ordinary evolutionary comparisons begin to collapse. A technological civilization might anchor itself around such a star not for one age but for many, watching galaxies change structure, watching stellar neighborhoods thin, watching the broader universe become less crowded with active suns, all while the local star continues its patient work. The meaning of home would deepen under those conditions. Home would not be merely a place in space, it would be a position within the surviving fraction of cosmic time. There is also a deeper cosmological quiet in this arrangement. The universe is expanding, and on the longest scales that expansion changes what can remain visible or reachable from any given gravitationally bound system. Distant galaxies recede. The wider cosmos becomes harder to observe directly. The local environment matters more. In a still more remote future, a civilization living around a red dwarf may find itself inside a universe that feels physically smaller in practical terms. Not because the cosmos has contracted, but because the expansion has carried so much beyond observational or causal convenience. In such a setting, the nearby star acquires even greater weight. It is not just a source of light in a populated universe. It is part of a shrinking island of relevance, one of the final reliable structures around which local complexity can remain organized. The red dwarf becomes not merely a star, but a center of remaining immediacy in a cosmos whose grander distances have become increasingly remote. Yet even this long reprieve is finite. Red dwarfs do not escape thermodynamic decline. They postpone its visible consequences, one by one, over eras so extended that language struggles to remain useful. Even these stars exhaust their hydrogen. Their fusion stops. Their white dwarf remnants begin the long cooling already waiting beyond the present age. The transition is scattered across time, not synchronized, but the direction is unmistakable. The last active stars in the universe will very likely be red dwarfs, because no other normal stars are built to endure so long. When the final one dies, the universe does not end, but the old familiar mode of cosmic brightness does. The stelliferous era gives way to something colder, more residual, and far less hospitable to chemistry powered directly by living stars. After that, heat still exists in remnants, in collisions, in accretion, in rare events and long cooling, but the age in which hydrogen-burning suns can easily anchor living worlds has effectively passed. That is the true scale of the red dwarf story. It begins with stars so dim that none can be seen with the naked eye, and it ends with those same stars serving as the final ordinary lights before the universe enters its deeper dark. Their smallness never stops mattering. Their faintness never stops mattering. But in the end, both qualities become secondary to endurance. Red dwarfs inherit the future because they are conservative with energy in a cosmos where conservation becomes destiny. When the bright ages are over, what remains is not the memory of the most luminous stars alone, but the long, slow work of the least conspicuous ones, still holding pockets of warmth against the cold for as long as any star can. That is why they are more than a class of small stars. They are the last extended bridge between a universe filled with suns and a universe living mostly on the remnants of what suns once were. And by the time that bridge finally fails, the history of everything familiar will already lie unimaginably far behind, preserved only in the patient fact that the smallest stars kept the lights on longer than anything else ever could. The long future of the universe does not belong to the stars that burn most brightly. It belongs, for a while, to the ones that endure. Red dwarfs seem modest when measured against the grandeur of giant stars, yet their true significance appears only when time is allowed to widen far beyond ordinary imagination. They are small enough to hide from the naked eye, cool enough to seem almost minor, and common enough to fill the galaxy without calling attention to themselves. But those same quiet qualities let them preserve something rare continuity. Around them, worlds may struggle with tidal locking, stellar activity, and narrow margins of habitability. Some will fail, some may remain barren, and some, perhaps, may hold on. If any do, they could inherit stretches of stable time so long that all of Earth's history would seem brief beside them. In that sense, red dwarfs are not simply faint stars at the bottom of the stellar scale. They are the slow reserve of the cosmos, the careful keepers of hydrogen fire, the last ordinary suns likely to remain when brighter ages have passed into memory. Their story begins at the edge of what can even count as a star, and it ends only after trillions of years of restrained persistence, when even they must finally cool into silence. Between those two limits lies one of the strangest and most humbling truths in astronomy, that the smallest stars may shape the longest future, not through violence or brilliance, but through patience, and somewhere in that patience lies their deeper mystery. They remind the universe that endurance has its own kind of power, and that the faintest lights may sometimes be the ones that remain when almost everything else has gone dark.